It's my belief that the advent of new media art is best regarded as a revolutionary event rather than as the outcome of a gradual evolutionary process. Not since the invention of the camera has a new technology come along which has changed the very fabric of art-making possibilities and the way artists think and work. As a result, the conjunction that now exists between the visual arts and new technology offers a rich seam of creativity that can help to drive forward progress on the major issues of the day. This is why I see new media art as being a newfound vehicle for research and innovation. My introduction to new media art was at the Cybernetic Serendipity exhibition, held as long ago as 1968 at the Institute of Contemporary Arts in London. There, I came across Gordon Pask's Colloquy of Mobiles. What you're seeing here is a replica produced recently by Paul Pangaro and his students at the College of Creative Studies in Detroit, a result that I'm sure would have delighted Gordon Pask. It reveals a group of objects, mobiles in fact, that can engage in a discourse where they compete, cooperate, and learn from one another, just like humans. Gordon Pask, as a mechanical philosopher, was far ahead of his time in getting machines talking to machines in a moving story of interaction. Only now are we beginning to catch up with this maverick genius in tackling similar exceedingly complex systems. So what do I mean by exceedingly complex systems? This was a phrase used by Stafford Beer, another UK cyberneticist, who in 1959 prepared an analysis of comparative systems. That is, what do organizational systems do and how do they do it, by classifying them from simple to complex. He exhibited a wry sense of humor in preparing his list and placed only 3 systems in his exceedingly complex category: the economy, the brain, and the company. In retrospect, Gordon Pask's colloquy, in being a work of art in process rather than a work of art as object, can be seen as an early attempt to simulate the system of how we think, how the human brain works. If he were to be alive now, I feel sure that Beer would place climate change on his exceedingly complex shortlist, in the knowledge that changes occurring in this system pose a formidable challenge, thus providing a platform where almost more than anywhere else there are opportunities for new media artists to drive forward innovation. I aim to talk about these opportunities, but first, to start my story, I'm casting my mind back to when my own interest in how we think was first ignited. This happened when I mentored a project called Biotica, an entry to the Wellcome Trust's S+T+ARTS scheme, submitted as long ago as the mid-1990s. Initiated by Igor Alexander, scientist, and Richard Brown, artist, Biotica was a project that incorporated neural nets in a dynamic, computer-generated form of artificial life. An immediate spin-off from Biotica was Millie the neural net starfish. People reached out to the starfish, and a tentacle moved towards them. You could swear that the creature had a brain and a mind of its own. At the time, my conversations with Richard and Igor extended far beyond starfish to embrace the puzzle of how to build a thinking machine. Igor, as Professor of Neural System Engineering at Imperial College, London, believed implicitly in the possibility of making a machine that mimicked the human brain. In his book, How to Build a Mind, he described the brain as being dependent on an unexplored form of engineering, one inspired by an astonishingly intricate structure or architecture. Some years later, I explored for myself the astonishingly intricate pattern of connections that underlies our ability to think. To find a clue, I turned to Islamic geometry. Islamic designs can not only confound the eye of the beholder with their complexity, but also they can provide a geometric clue to solving complex spatial problems. Further, they generate networks where the lines of the mathematical scheme can be regarded as a system of neural communication. By taking a very small section of the brain as an example, we can begin to see a pattern producing a multitude of ribbons that interweave one with another in designs of dazzling complexity. You can see here the radiating centers, or hubs, of my chosen pattern, generating a multitude of interconnecting ribbons, or axons. Of course, we all know that the brain's grey matter doesn't present that degree of geometric precision. But when the same pattern is distorted, as if by the brain's giri, or hills, and sulci, or valleys, we see something much more random. Such distortions, or synaptic ballets as I call them, form the basis of a recent piece of visual music called brainwaves. You'll be seeing and hearing that soon. But first, I want to share an earlier piece with you, Turingalila, that I now see as being pivotal in bringing my separate interests in the realms of science and new media art closer together. In Turingalila, I celebrated Alan Turing's work on morphogenesis by perturbing Turing patterns to reveal processes of self-organization reminiscent of those found in nature. Let's look at what happens in just one movement from Turingalila, my piece of visual music on the theme of morphogenesis. In that movement, and the other two that I haven't shown you, an extraordinary diversity of forms emerged seemingly spontaneously from my perturbations. I appear to have hit on a purposeful tool for simulating natural processes. Whenever I perform Turingalila, always I make special mention of the work of Professor Jeremy Green, a developmental biologist at King's College, London. He is that rare exception, a biologist who has fully embraced the concept of self-organization in regulatory networks, occurring in tandem with the chance outcomes of Darwinian selection. As my scientific mentor on Turing's morphogenesis theory, and much more besides, I've learned much from him over the years. In fact, it was his enthusiasm for Turingalila that set me off on a subsequent search into the patterns that underlie how our brains work. You will understand, therefore, why I was eager to know what Jeremy might make of my Islamic conjecture. You can see his comments here. Clearly, my conjecture was not a conclusion, but maybe just another step towards making the invisible visible. Note that Jeremy refers in particular to connections and the extent to which any given pattern can facilitate the myriad of connections that underpin the workings of the human brain. I now discover that at Harvard University's Lichtman Lab, the idea that connections are everything in cognition has sparked off a new field of neuroscience called connectomics. It involves a novel means of cutting brains into very thin slices, which, through images acquired at unprecedented speed by a new type of electron microscope, enables every synaptic connection between nerve cells to become visible. Glimpses of the brain's intricate architecture coming out of this work reveal networks of a greater complexity than has ever previously been imagined. The digital outputs of connectomics produces big data, unprecedented quantities of information at unprecedented rates. All this happened some time ago, in 2014. But even now, neuroscience lacks the organizing principles or a theoretical framework for converting brain data into fundamental knowledge and understanding. Big data presents a paradox. In the process of gaining ever more information on what we are seeking, we lose sight of where we're going. Yves Freniac of the French National Centre for Scientific Research expresses this thought very eloquently, as you see here. Clearly, connectomics has reached an impasse. It's a project that serves to remind us that digital computation is the most potent creation that the human brain has ever come up with. Its intelligences are now surging ahead of our more slowly evolving human brain's capacity to keep up and to understand what technology is telling us. As of a few years ago, Jeff Lichtman's view, lacking a clear idea on what parts of the connectomics data trove might ultimately be relevant, was to err on the side of getting too much data rather than just the data that might answer a particular question. But this view serves only to compound the big data problem by increasing exponentially the requirement for the storage and analysis of massive amounts of digital information. Now, don't think that I'm underrating in any way the spectacular work generated by the Lichtman Lab. Any project that has developed automated methods for both generating and analyzing digital datasets that reveal all the neural wiring between nerve cells and many subcellular details of brain tissues deserves respect and serious consideration. But I can't help thinking that there must be a better way of gaining an understanding of an exceedingly complex system like the brain. What is it? Jeremy Green, I think, provides a clue when he explained his own processes of research and discovery into how complex anatomy emerges from the simplicity of just a single fertilized egg. He later compared his method to that of an artist wrestling with the constraints of a medium, whatever it might be, as a creative act that brings out novelty and insight. You can guess, of course, why I thought this description was spot on. The idea that an answer to extreme complexity lies in the continual testing of data against a preconceived model or conjecture does indeed describe my own method of work as a new media artist, and for that matter, the method of many other new media artists. If data doesn't match any given conjecture, then one of them must be wrong, and you have something to learn. Many conjectures are needed during the process of penetrating the mysteries of the brain, and just possibly, in leaping the barriers imposed by big data, my Islamic conjecture could be one of them. I'm proposing a specific type of structural connectivity that appears to favour and enable the emergence of highly complex and variable dynamic patterns. So variable, in fact, that at first glance they give no sense of commonality or coherence, although, in spite of appearances, each pattern conforms strictly to the same underlying Islamic geometry. My visual music piece, Brainwaves, demonstrates this idea. Within that quickly moving imagery, you will have glimpsed just a few of the brain's 100 trillion or so synaptic interconnections. I feel bound to pause here to ask, am I deceiving myself, or have I entered a world of fantasy? Possibly I've done just that. But don't forget Nabokov's poetic words, where he states, there's no science without fantasy, and no art without facts. To my mind, there's enough factual reality in brainwaves for me to make a plausible claim that it provides a valid, albeit disruptive, artistic insight on how our brains might work. Nobody as yet knows the answer. Experts on brain connectivity understand the challenges the brain has to meet, but they don't know how it does it. There's still a long way to go. Those of us who are proponents of conjectures must accept the often short-lived and transient usefulness of our ideas. Only very few will give some indication that they merit further and often expensive investigation to become eventually the basis of general scientific theory. It's in support of such an ideas-led process of discovery, where conjectures come first, that I like this quote from the letters of Yakov Ilyich Frenkel. His definition of a good caricature has meaning because it brings to the surface the not quite obvious. It can offer a distortional twist that can throw some new light on a problem obscured by a surfeit of information or burdensome detail. When tackling any of the 17 United Nations Sustainable Development Goals, for instance, caricatures can be drawn at multiple instances during research and development processes. Much value can be gained when they are produced not only by scientists and technologists, but also by new media artists with a proven creative curiosity. It's by taking this collective approach that bottlenecks caused by a surfeit of big data can be released, a benefit that applies particularly in large-scale research studies into complex systems, like the brain and climate change. It's by reference to my own immersion in the exceedingly complex system of the brain that I've sought to reveal how an apparently disruptive idea from the world of art can act as a trigger which, in providing a conjectural plateau of lucidity, might be able to assist in moving processes of research and innovation forward. As we've seen, the process of biological discovery, that is connectomics, produces a mass of information that is difficult to unravel. But work continues worldwide into solving the riddle. More recent conjectures, spun off by mathematics in the form of algebraic topology, are beginning to provide new insights into the complexities of many separate components of the brain. What's been discovered so far is the existence of all-to-all connected nodes called cliques. Using the language of algebraic topology, cliques become simplices or hypertetrahedrons. In the cliques I'm showing here, you can see a 6-dimensional and a 7-dimensional simplex expressed as directed graphs. They're called directed graphs because they trace the pattern of information flow within the brain's microcircuits. You'll have noticed, I think, the geometric resemblance between cliques and the hubs of the Islamic pattern I showed earlier. It's a similarity that must be regarded as coincidental, of course, but nonetheless remarkable. The hubs of my chosen Islamic pattern require an 11-dimensional simplex to provide maximum information flow. This star-like result is not just a fiction. Recent reports of in vivo investigations have noted star-like configurations within the brain's network. Stars appear to be useful configurations for achieving fast communication between the 83 regions of the brain. These same star-like elements signify not only cliques, but also cavities. In its simplest form, a cavity can be formed within a geometric object defined by just 2 tetrahedrons. At the other extreme, the formation of a net of tetrahedrons can generate a vast number of potential synaptic communication routes. Together, the topological notions of dense cliques and information distributing cavities are beginning to unravel the complexities of an exceedingly complex system. For the moment, only fantasy can put a form to the idea, as you see here. What remains to be discovered is a new type of geometry, which in putting all the parts together can shine a light on how a multidimensional synaptic network can accommodate ever-changing patterns of neural density as they occur in different regions of the brain. That's still quite some task. Now, I don't want you to get the wrong impression. I'm not claiming that my Islamic pattern is the answer. Far from it. It is only one of many conjectures, conceived during a long and continuing process of discovery that might merit some further investigation. The fact that the idea has emerged from the realm of new media art, rather than science, underlies my main purpose in giving this presentation: to lay stress on the importance and potential value of involving new media artists in programs of research and innovation. In my experience, the creative processes of art and science are similar to the point of being virtually synonymous. As I've shown in this presentation, patterns, the seeing of patterns, the making of patterns, and the interpretation of patterns can provide a common language of communication in tackling complex problems. For scientists and artists alike, it's the coherence and lucidity of patterns that provides a starting point for gaining understanding and formulating action. The result is a shared creative environment where new media artists think and create like scientists, scientists think and create like new media artists, and the digital tools of discovery and expression that they each use are one and the same. Exceedingly complex problems have common characteristics. They are composed of a huge number of and a great variety of components, which at first glance appear to be irreconcilable, one with another. In drawing parallels between the challenges to understanding presented by the brain and the similarly daunting task of tackling climate change, it becomes apparent that more than ever there is a need for research and innovation procedures to be conducted by what George Steiner calls a code of the collective, where the two great ways of knowing, understanding, and discovery, art and science, need to be creatively and closely harnessed together. When Bill Gates, in his recent book, How to Avoid a Climate Disaster, tells us that to find solutions we'll need biology, chemistry, physics, political science, economics, engineering, and the other sciences, he's missing out the other crucial 50%, all those involved in the arts and humanities. This mustn't be allowed to happen. All the more significant, therefore, that the European Commission has set up its S+T+ARTS initiative. This is a progressive initiative that aims to support collaborations between artists, scientists, engineers, and researchers to develop more creative, inclusive, and sustainable technologies. Now, through S+T+ARTS and opportunities offered by the European Commission's initiatives, new media artists can be expected to join their scientific and technological counterparts in generating and developing ideas that can not only transform our use of nature's resources, but also act as a behavioral trigger in promoting awareness and changing attitudes towards the ravages of climate change. Thank you for watching